Look around you. The materials you interact with every single day are almost never pure, isolated chemical substances. The idea of elemental purity is mostly a myth. True single-element materials are largely theoretical, or at best confined to highly controlled laboratory environments. The vast majority of the materials we actually rely on, the air we breathe, the structural metals we build with, even the fluids pumping through our bodies, are complex mixtures. The function and utility of every one of these everyday materials are entirely dictated by their exact chemical composition. To understand how the material world actually works, we must look past the idea of purity and master the mechanics of these complex mixtures. Consider the engineering of alloys. By taking the exact same base metals and introducing different trace additives, you create entirely distinct materials. If you mix copper and zinc, you get brass. But introduce nickel to that exact same mixture, and you have German silver. Swap the nickel for tin, and you forged bronze. These minute compositional changes dictate the physical properties of metals at a massive industrial scale. But this dependency on exact composition isn't limited to blast furnaces and heavy industry. It governs the highly sensitive biological systems inside you. Human biology runs entirely on highly specific liquid mixtures that must remain in perfect continuous balance to sustain life. When a patient is administered intravenous fluids, that bag suspended above them cannot simply contain pure water. Injecting pure water straight into the bloodstream would immediately cause severe cellular damage. Instead, those IV injections must contain specific salts, meticulously dissolved at precise ionic concentrations that perfectly match the patient's existing blood plasma. Whether forging industrial metals or sustaining biological life, exact compositional ratios are the hidden variables dictating success or failure. To understand these variables, we need to narrow our focus from generic mixtures down to a highly specific, highly ordered class of chemical mixtures known as solutions. The absolute fundamental requirement for a chemical mixture to be classified as a solution is that it must be homogeneous. Mechanically, homogeneity means two distinct substances blend together until their composition and physical properties are perfectly uniform all the way down to the microscopic level. The simplest architectural form this takes is a binary solution. This is a framework containing strictly two components. Within this binary pairing, the component present in the largest quantity is the solvent. The solvent dictates the terms of the relationship. It acts as the structural master, strictly determining the final physical state, whether solid, liquid, or gas, for the entire solution. The secondary, minority component is the solute. It surrenders its original physical state to become uniformly dispersed within the structural grid established by the solvent. A solution represents a microscopic architectural takeover, where the dominant solvent forces the solute to conform completely to its physical face. While many assume that dissolving strictly involves mixing a solid powder into a liquid solvent, the reality is much broader. This table breaks down the complete matrix of physical phase combinations. Because the solvent has total authority over the final state, binary solutions can actually form 9 distinct variations. Looking at the top 3 rows, we see gaseous solutions. Here, a gas acts as the solvent, capable of dissolving other gases or even suspending solids, like camphor, uniformly within it. Moving to the middle section, we find the liquid solutions. This is the most common biological context, where gases like oxygen or liquids like ethanol dissolve seamlessly into water. But the bottom 3 rows reveal something highly counterintuitive: solid solutions. Under the right conditions, gases or liquids can perfectly dissolve into a solid metallic matrix. High-end jewelry relies entirely on this solid-state dissolving process to achieve its durability and color. That ring is rarely pure gold. It is a solid solution, where a metal like copper acts as a solute, completely and uniformly dissolved within the gold solvent. Discarding our inherent liquid bias and relying purely on the strict rules of uniformity reveals a complete 9-phase matrix of possible materials. Once the physical state of a solution is locked in by the solvent, its practical function in the real world is determined by ultra-fine mathematical variations in its concentration. To track these life-altering ratios, we have to use microscopic measurement scales, like parts per million, or ppm. We can see this razor-thin margin by tracking the exact concentration of fluoride ions dissolved in a standard water solvent. At exactly 1 part per million, the dissolved fluoride acts as a protective medical agent, perfectly optimized to prevent human tooth decay. But if you increase that concentration by a mere half point to 1.5 parts per million, the biological effect flips entirely, causing dental enamel to become visibly mottled and damaged. Now watch what happens when the concentration of those exact same ions is dialed up significantly. At high concentrations, this same simple binary solution of sodium fluoride becomes a highly lethal compound, routinely used in rat poison. In physical chemistry, mathematical ratios alone dictate whether a substance functions as a medicine, a source of damage, or a lethal poison. Our constructed world is built entirely on mixtures, strictly governed by the dominant physics of the solvent and the uniform surrender of the solute. Classifying a material into the 9-phase matrix is just the first observational step. The next scientific hurdle is moving from qualitative descriptions to rigorous mathematical quantification, expressing these concentrations in standardized units. Mastering these standardized measurements is the only way to predict advanced chemical behaviors, setting the stage for understanding vapor pressure and the colligative properties of solutions. Watch this dark particulate matter dissolve into the clear liquid. Qualitatively, we describe the initial clear liquid as dilute, meaning it holds a small quantity of solute. As more matter dissolves, it becomes concentrated, holding a relatively large quantity of solute. In a real-world chemical application, those descriptions are useless. A label of concentrated carries no numerical precision. Controlling a chemical reaction requires exact parameters. A chemist must know the specific mathematical ratio of a single active component relative to the entire liquid system. To achieve this precision, chemists rely on a specific matrix of formulas to quantify mixtures mathematically. Without precise quantitative concentration metrics, ensuring safety in industrial chemistry or determining a safe pharmacological dose is impossible. The ambiguities of human language are too dangerous for the laboratory. This diagram organizes the 7 equations used to quantitatively describe a solution, from mass percentage to molality. Notice the isolated denominators. Some measure mass, others volume, and others count atoms. Why does chemistry require 7 redundant formulas for concentration? These are not alternate preferences. Each formula exists to solve a specific scaling challenge or physical problem that the others cannot handle. A chemist's choice of metric is strictly dictated by the solution's physical state, the extreme precision required, and the thermodynamic environment of the laboratory itself. The wrong metric misrepresents the solution's physical state as laboratory conditions shift. The most intuitive metrics rely on ratios built from easily measurable macroscopic properties, mass and volume. This formula builds mass percentage, or W over W. It is exactly what it sounds like: the mass of a specific component divided by the total mass of the solution, multiplied by 100. Commercial bleaching solutions, for example, typically contain as 3.62 mass percentage of sodium hypochlorite dissolved in water. By swapping the variables, we get volume percentage, or V over V, the volume of the component divided by the total solution volume, multiplied by 100. Standard for liquid solutions, a 35% volume-to-volume solution of ethylene glycol acts as an antifreeze, lowering water's freezing point to cool car engines. There is a third combination, mass by volume percentage, or W over V. This calculates the mass of solute dissolved in exactly 100 milliliters of solution. This specific mass-to-volume metric is the standardized language of pharmacy and medicine for formulating dosages. These percentage metrics work perfectly for manufacturing and macroscopic dosing, but they lack the atomic-level specificity a chemist needs to actually predict how 2 chemicals will react. When we shift to environmental and trace analysis, percentage models break down, resulting in decimals burdened with endless zeros. For trace quantities, we use this formula, parts per million, or ppm. We divide the parts of the component by the total parts and multiply by 1 million. Parts per million is flexible. Those parts can be expressed as mass to mass, volume to volume, or mass to volume depending on the required medium. Consider seawater. A 1-liter sample weighs 1,030 grams, but it contains roughly 6 times 10 to the negative third grams of dissolved oxygen. Expressing that as a percentage creates an unreadable fraction. Translated into parts per million, it becomes 5.8 grams per million grams of seawater. Parts per million acts as a mathematical magnification tool. It scales trace elements up to whole numbers without altering the underlying ratio. To execute accurate stoichiometric calculations, chemists must abandon macroscopic mass entirely.
They have to count the actual molecules in the beaker using moles. This is mole fraction, denoted by the symbol X. It represents the exact ratio of the moles of one component to the total number of moles of all components in the system. To find the mole fraction of a 20% mass solution of ethylene glycol, we convert raw masses to moles. 20 grams divided by its molar mass of 62 grams per mole gives 0.322 moles. The 80 grams of water translates to 4.444 moles. Plugging those mole values into our fraction yields a mole fraction of 0.068 for the ethylene glycol. The math rests on one strict rule. The sum of all mole fractions in a given solution always equals exactly 1. This unit is exceptionally useful for isolating the physical properties of gas mixtures and determining vapor pressure in sealed containers. Mole fraction strips away the illusion of size and mass. It reveals the true atomic proportions of the mixture. The most common unit for daily laboratory work involving liquid solutions is molarity. Molarity, denoted by a capital M, is defined precisely. It is the number of moles of solute dissolved in exactly 1 liter of solution. Take a solution containing 5 grams of sodium hydroxide in 450 milliliters total volume. First, the 5 grams converts to 0.125 moles. Divide that by 0.450 liters, and you have a 0.278 molar solution. Because molarity relies on liters, it is perfectly suited for fast, volumetric liquid dispensing using standard graduated lab glassware. Molarity is highly convenient for liquids at room temperature, but it hides a critical thermodynamic vulnerability. To expose that vulnerability, we look to the final metric, molality, denoted by a lowercase m. Compare the two. While molarity measures per liter of solution, molality measures the number of moles of solute per kilogram of the solvent. Look at the liquid level inside this heated flask. Why do chemists need both formulas when they measure almost the same thing? As temperature increases, liquids thermally expand. The total volume of the solution increases, even though the number of atoms inside remains identical. Because molarity's denominator is volume, heating a 1.0 molar solution mathematically lowers its calculated concentration. The metric skews as the room warms. Molarity is entirely a function of temperature. If an experiment requires extreme heat or freezing conditions, molarity becomes dangerously unreliable. To master chemical concentrations, we must categorize these metrics not by what they measure, but by how they react to the environment around them. Mass percentage, parts per million, mole fraction, and molality separate into a unified category, temperature independent. Because these 4 metrics rely exclusively on mass measurements or raw particle counts, they are completely immune to temperature fluctuations. A kilogram of water is a kilogram of water, whether it is boiling or near freezing. Conversely, molarity and volume percentage fall into the temperature-dependent category. Any metric containing volume in its equation is inherently tied to the thermal state of the room, requiring strict environmental control to maintain accuracy. The practical rules of the laboratory are clear. Use molarity for standard room temperature titrations where speed and liquid volume are priorities. But for testing boiling point elevation, freezing point depression, or working in field environments with fluctuating heat, molality or mass-based metrics are strictly required. Chemistry is the act of anticipating the physical constraints of the universe. Understanding the anatomy of these 7 formulas guarantees that a chemist chooses a metric that doesn't just describe a mixture, but survives the conditions of the experiment. Stirring sugar into a glass of water looks entirely peaceful, but that exact same physical process, a substance dissolving into a fluid, is the mechanism behind a catastrophic, life-threatening event, the sudden, uncontrolled eruption of nitrogen gas bubbles inside a diver's bloodstream. To understand why, we have to discard the intuitive, everyday model of solubility.
When a solid or gas dissolves in a liquid, it doesn't simply vanish into empty spaces between the water molecules until the container is full. A liquid is not a static parking lot. Instead, dissolution is a continuous, active state. It is a state of dynamic equilibrium. The physics of this state are governed by a specific, reversible equation. Solute plus solvent yields a solution. But the arrows here indicate a two-way street. When you add a solid to a liquid, particles break away and enter the solution. But simultaneously, dissolved particles in the fluid collide with the remaining solid and reattach themselves in a process called crystallization. The equilibrium point is reached strictly when these two opposing rates perfectly match. At this exact threshold, even though millions of individual particles are swapping places every second, the overall concentration of the dissolved substance stops changing entirely. We call this a saturated solution. Because solubility relies on this active mechanical balance rather than a fixed physical capacity, the system can be predictably manipulated. We can shift the equilibrium, forcing a fluid to absorb or expel a substance by pulling two thermodynamic levers, temperature and pressure. Before we pull those levers, we have to account for the physical structures of the matter involved. Solids and liquids have drastically different molecular architectures than gases. The atoms in a solid block of salt, or a pool of liquid water, are already densely packed together. There is very little empty space remaining between them. Because of this tight packing, solids and liquids are highly incompressible. As a direct result, altering atmospheric pressure has virtually zero effect on the solubility of a solid. Squeezing the water won't force it to accept more dissolved salt. Gases operate under completely different rules. Gas molecules are widely dispersed, making them highly compressible and extremely sensitive to changes in external pressure. To control the behavior of dissolved gases, whether in an industrial plant or human veins, we must master exactly how pressure and temperature force this delicate dynamic equilibrium to shift. The rules governing how dynamic equilibriums respond to systemic stress are defined by Le Chatelier's principle. If dissolving a nearly saturated solid into a liquid requires the absorption of heat, an endothermic process, then pumping heat into the system drives the equilibrium forward. The liquid will dissolve more of the solid. But dissolving a gas into a liquid acts in reverse. The physical process of trapping widely spaced gas molecules into a dense fluid is analogous to condensation. It actually releases heat into the environment, making it an exothermic process. Because gas dissolution is exothermic, adding external heat acts as a systemic stressor. According to Le Chatelier's principle, the system will compensate by shifting the equilibrium backward. The liquid rejects the gas, forcing it to escape back into the air. This thermodynamic law dictates the distribution of the planet's biomass. Aquatic species thrive in high concentrations near the poles because cold water inherently holds far more dissolved oxygen than warm tropical currents. While ambient temperature dictates the baseline capacity of our oceans, manipulating gas solubility on a human timeline requires the blunt mechanical force of pressure. Consider a closed mechanical system, a pocket of gaseous atmosphere resting directly above a liquid solvent. In its baseline steady state, the system is balanced. Gas particles strike the liquid surface and dissolve at the exact same rate that already dissolved particles escape the liquid and return to the air. Now, a mechanical piston drops and compresses the gas into a fraction of its original volume. This compression drastically increases the number of gas particles per unit volume. With the particles packed so tightly together, the rate at which they physically strike the liquid surface multiplies.
This relentless bombardment mechanically forces more gas particles down into the liquid phase. The concentration inside the fluid rises until a new dynamic equilibrium is achieved at this higher pressure state. The physical compression of a gas forces a directly proportional increase in its solubility within the solvent beneath it. This mechanical relationship between compression and solubility was precisely quantified by William Henry in the early 19th century. Henry's law states that the partial pressure of a gas in the vapor phase, represented as P, is directly proportional to its mole fraction, or concentration, in the solution, represented as X. The bridge between these two variables is Kh, the Henry's law constant. This is a unique numerical fingerprint dictated by the specific chemical nature of each gas and solvent pair. The algebra dictates a critical inverse relationship. If the external pressure remains constant, a chemically higher KH value mathematically forces a lower solubility. This is a data table showing the specific Henry's law constants for several gases dissolved in water. To verify this mathematical relationship in reality, we can isolate nitrogen and oxygen. At a baseline temperature of 293 Kelvin, nitrogen's KH constant sits at a massive 76.48 kilobar, while oxygen's is less than half that, at 34.86. Because its constant is so much higher, nitrogen naturally dissolves far less readily in water than oxygen. If we move down the table and increase the ambient temperature to 303 Kelvin, nitrogen's constant jumps from 76.48 up to 88.84. This rising KH value in the raw data provides mathematical verification of our thermodynamic rule. As heat increases, the solubility of a gas drops. We manipulate this physical relationship constantly in mass market manufacturing. Inside commercial bottling plants, machinery artificially spikes the partial pressure of carbon dioxide directly above the fluid, forcing a high rate of solubility. The bottle is immediately sealed to lock that high-pressure equilibrium in place. But when human beings transition into extreme environments, the mechanics of Henry's law quickly turn lethal. At high elevations, climbers face a drastic subversion of the equation. As the atmospheric air thins out, the external partial pressure of oxygen drops severely. Because the external pressure has plummeted, Henry's law dictates that far less oxygen will dissolve into the bloodstream. This rapid drop in dissolved oxygen triggers severe weakness, confusion, and anoxia. Human survival relies on a strict, predictable atmospheric pressure to continuously force the required amount of oxygen into our blood. The most extreme stress test of Henry's law occurs deep underwater, where external pressure scales exponentially. To simply inflate their lungs against the crushing weight of the ocean, a scuba diver must breathe heavily pressurized air. Since standard air is mostly nitrogen, breathing it under compression artificially spikes the partial pressure of nitrogen in the lungs. Driven by the math of P equals KHX, massive quantities of nitrogen gas are forced to dissolve directly into the diver's bloodstream. The crisis hits if the diver swims too quickly toward the surface. As the depth decreases, the heavy external pressure suddenly lifts. Without that intense pressure holding the gas in solution, the dynamic equilibrium instantly shifts backward. The massive load of dissolved nitrogen separates out of the blood phase and rapidly expanding into hundreds of gaseous bubbles directly inside the diver's veins. These gas bubbles block the capillaries, creating an agonizing medical emergency known as decompression sickness, or the bends. It is a catastrophic biological failure caused by a rapid drop in partial pressure. To prevent this, deep-sea divers use a chemical engineering solution. They dilute the air mixture in their tanks with helium. Helium works because it possesses an inherently massive Henry's law constant. Even under the extreme pressure of the deep seafloor, helium's high KH value ensures its physical solubility remains incredibly low, preventing toxic concentrations from building up in the blood. Mastering the invisible mathematics of P equals KHX is how we engineer biological survival in environments where the physics of dissolution would otherwise be lethal. When we place a binary solution of two highly volatile liquids into a sealed glass vessel, both components begin to evaporate into the space above. This evaporation continues until the system reaches a precise state of phase equilibrium. At this exact point, the rate at which the liquid molecules escape into the vapor phase perfectly matches the rate at which vapor molecules condense back into the liquid. The gas trapped in this enclosed headspace exerts a measurable force against the container's walls. We define this physical force as the total vapor pressure. But this total pressure is actually a composite. It is the sum of the partial vapor pressures generated independently by component 1 and component 2, as they share the same physical space. To predict the total pressure of this invisible gas mixture, we have to shift our focus downward to the liquid phase. The gas dynamics are entirely dependent on the specific mathematical ratio of the two liquids in the solution below. Analyzing the liquid phase gives us the exact metrics needed to understand the vapor phase. We quantify the ratio of the two liquids using mole fractions, denoted as x1 and x2. These variables represent the proportion of each component's molecules relative to the total number of molecules in the solution. Because this is a strict binary system consisting of only two components, the sum of their mole fractions must always equal exactly 1. The critical question is how altering this specific ratio of liquid components dictates the individual partial pressures in the vapor phase above. By establishing a strict mathematical link between the liquid composition and the gas pressure, we can predict the behavior of the entire system purely from the measurements of the liquid. The French chemist François-Marie Raoult formalized this relationship in 1886. Raoult's law states that for volatile liquids, the partial vapor pressure of each component is directly proportional to its mole fraction within the solution. This coordinate plane maps the mathematical relationship. The x-axis represents mole fraction, and the y-axis tracks vapor pressure. Plotting component 1, its partial pressure starts at 0 and rises linearly as its mole fraction scales to a concentrated state, where x1 equals 1. The maximum point on this line represents the pure vapor pressure of component 1 at that specific temperature. Therefore, any component's partial pressure in a mixture is strictly bounded by two things: its physical concentration in the liquid and its inherent volatility in a pure state. We can run the exact same analysis for component 2, mapping its linear trajectory starting from the opposite end of the x-axis, where its mole fraction is 1. Looking at this updated graph, the distinct slope of component 2's line reveals something crucial. It reaches a significantly higher maximum point on the y-axis than component 1. Because component 2 has a higher pure vapor pressure ceiling, we define it as the more volatile liquid of the two. A higher pure vapor pressure indicates weaker intermolecular forces within that specific liquid, which allows a greater number of its molecules to escape into the gas phase at a given temperature. The inherent physical properties of the pure liquids set the absolute boundaries for how their combined mixture will behave. To find the total pressure of the system, we apply Dalton's law of partial pressures, which states that the total pressure over the solution is simply the sum of the individual partial pressures. Visually, we translate this algebraic addition into geometry by stacking the heights of line I and line 2 at any given mole fraction, creating a new solid line that connects the two pure vapor pressure peaks. Mathematically, we substitute the partial pressures in Dalton's equation with their Raoult's law equivalents, the pure vapor pressure of each component multiplied by its mole fraction. Because the mole fractions must equal 1, we can simplify this substitution to arrive at a single, unified equation. The total pressure equals the pure pressure of component 1 plus the difference between the two pure pressures multiplied by the mole fraction of component 2. This formula proves that the total vapor pressure over the entire solution varies linearly with the mole fraction of the more volatile component. The total environmental pressure of the mixture is anchored entirely by the pure state properties of its constituents. We can test this theoretical model against a real-world chemical dataset using two widely utilized industrial solvents. We will use chloroform, which has a pure vapor pressure of 200 millimeters of mercury at 298 Kelvin, and dichloromethane, which sits at 415 millimeters of mercury at the same temperature. Based on those pure pressure values, dichloromethane is clearly the more volatile component. Our physical system begins by mixing 25.5 grams of chloroform with 40 grams of dichloromethane. Our goal is to use only the mass of these starting liquids to accurately calculate the total environmental pressure of the gas phase above them. First, we divide the mass of each liquid by its molar mass to convert our input into moles. This gives us 0.213 moles of chloroform and 0.47 moles of dichloroform. Dividing those individual values by the total number of moles yields our liquid mole fractions, 0.688 for dichloroform and 0.312 for chloroform. We then plug the mole fraction of our highly volatile dichloroform, along with the two known pure pressures, directly into our derived linear equation. The math resolves to a calculated total system pressure of exactly 347.9 millimeters of mercury. By utilizing Raoult's and Dalton's laws, the theoretical model successfully predicts the macro pressure of the environment using only the microdata of the liquid. We can push this analysis one step further to determine the exact composition of the gas phase itself,
using the relation that a vapor mole fraction equals its partial pressure divided by the total pressure. Running this calculation reveals the vapor mole fractions, 0.82 for dichloroform and 0.18 for chloroform. These side-by-side bar charts compare the original liquid concentration against the resulting gas. The dichloromethane goes from making up 68.8% of the liquid to a massive 82% of the vapor. The vapor phase has become significantly richer in the more volatile component than the liquid phase below it. This demonstrates a strict thermodynamic rule. At equilibrium, the more volatile component will always dominate the gas phase.
When chemists mix different substances together, the immediate priority is predicting exactly how that new solution will behave. To do this, we rely on a strictly defined relationship. The partial pressure of any component in a mixture is directly proportional to its mole fraction in that solution. Textbooks often introduce a point of confusion here by presenting two entirely separate laws to describe this single mathematical reality. If you are dissolving a gas into a liquid, you use Henry's law. But if you are dissolving a volatile liquid into another liquid, you are told to use Raoult's law. Look at these two equations side by side. The variables for partial pressure on the left side of the equal sign and mole fraction on the right are functionally identical in both formulas. The only distinction is the proportionality constant. In Henry's law, that constant is Kh. In Raoult's law, Kh is simply replaced by Pi0, the vapor pressure of the pure solvent. Because the underlying mathematical relationship is exactly the same, Raoult's law operates entirely as a special boundary case of Henry's law. To see exactly why these equations converge, we need to step away from the algebra and examine the physical, statistical geometry occurring at the very surface of a liquid. Evaporation is a violent mechanical process. Molecules at a liquid's boundary constantly vibrate, eventually breaking free and launching upward into the gas phase. We can observe this clearly by looking at a pure liquid solvent held at a constant temperature inside a sealed container. At the surface boundary of this liquid, solvent molecules continuously escape into the empty space above. Simultaneously, those vaporized molecules bounce around the container. Some of them collide with the liquid surface and are recaptured, a process called condensation. Eventually, the system reaches a state of dynamic equilibrium. This occurs at the exact moment the rate of evaporation perfectly matches the rate of condensation. This diagram shows that exact state. Notice that the entire top layer consists exclusively of uniform solvent molecules. The physical pressure exerted by gas molecules bouncing against container walls during this equilibrium state is defined as the vapor pressure of the pure liquid. The pure liquid achieves its maximum potential escape rate, and therefore its maximum vapor pressure, because it has 100% undisputed access to the surface area. Now we introduce a solid solute, like sodium chloride or glucose, directly into the pure solvent. These solids are non-volatile. Their particles will not evaporate, meaning they cannot physically enter the gas phase and contribute to the pressure above. These non-volatile particles distribute evenly throughout the solvent, taking up prominent positions along the top surface boundary. The surface is a shared zone. Solute particles take physical space, meaning the fraction of the surface covered by solvent molecules is permanently reduced. The mechanical consequence of this shared surface is immediate. Fewer solvent molecules are physically exposed to the boundary. With fewer pathways to the surface, the total number of solvent molecules capable of escaping into the gas phase drops. This drop in the evaporation rate breaks the previous dynamic equilibrium. With fewer gas molecules in the space above the liquid, the total pressure exerted by the vapor drops. This lower reading is the vapor pressure of the new solution. Vapor pressure lowering requires no complex chemical transformations. It is a simple statistical roadblock caused by solute particles physically blocking the exit. This mechanical model prompts a logical question. Does the specific chemical identity of the solid dropped into the liquid alter how much the pressure drops? We can answer this by looking at laboratory data comparing two vastly different chemicals, sucrose and urea. Adding 1.0 mole of sucrose to 1 kilogram of water lowers the vapor pressure exactly as much as adding 1.0 mole of urea. This diagram compares the two solutions. Sucrose molecules are large and complex, while urea molecules are small and simple. Yet, because we added the same number of moles, they occupy the exact same number of geometric slots at the surface. Vapor pressure depends entirely on the fraction of the surface covered. The physical shape or mass of the blocking particles has no impact on the outcome. Only the raw number of particles matters. In the thermodynamics of colligative properties, chemical identity is irrelevant. The physics relies strictly on the particle count. To map the behavior of these beakers into a predictable system, we need a mathematical model that charts this statistical surface coverage. This is a coordinate graph plotting vapor pressure on the y-axis against the mole fraction of the solvent, labeled x1, on the x-axis. We start at the origin, where x1 equals 0. If the mole fraction of the solvent is 0, there are no solvent molecules present to evaporate. The resulting vapor pressure is 0. Now we plot the maximum extreme. At an x1 value of 1, the solution is pure solvent. With 100% surface coverage, the solvent reaches its maximum theoretical escape rate, hitting the pure vapor pressure point of P10. Connecting these two states reveals a perfectly straight line. The equation for this line is P1 equals x1 P10. This gives us Raoult's law in its general form. The partial vapor pressure of any volatile component is directly linearly proportional to its mole fraction in the solution. Raoult's equation is a direct mathematical translation of a physical reality. The geometry of a liquid's surface dictates the pressure of the gas above it.
Industrial chemical separation rests on a straightforward premise. If you have a mixture of two liquids, they will boil at different temperatures. When engineers need to extract alcohol from a fermented batch of ethanol and water, they use fractional distillation. They heat the mixture to exploit the temperature gap between the two boiling points, driving the more volatile alcohol into a vapor state. If you continuously boil off that vapor and condense it in a separate chamber, the math suggests you should eventually isolate 100% pure ethanol. But the process always stops working. Distillation hits an insurmountable physical limit at exactly 95% ethanol concentration. Once the mixture reaches that 95% ratio, the liquid stops separating. The vapor rising from the boiling mixture contains the exact same 95:5 ratio as the liquid left behind. Chemists call this an azeotrope. It is a constant boiling mixture that completely breaks the standard mechanics of separation. At this specific concentration, the separate liquids begin to behave like a single, indivisible pure compound. The industrial equipment hasn't failed. To see why distillation stops, we have to scale down and look at the thermodynamics of how these molecules interact with each other. Every liquid is governed by the strength of its intermolecular attractive forces. If we isolate a pure liquid A and a pure liquid B, the molecules in each respective container are held together by their own self-interactions. A molecules are attracted to other A molecules, and B to B. When you pour them together, you force those molecules to interact. They physically mingle to form a uniform binary solution. In a theoretical scenario called an ideal solution, the new attractive forces between an A molecule and a B molecule are exactly equal to the original A to A and B to B attractions. When this precise balance exists, the enthalpy of mixing is 0. That means the act of mixing the liquids absorbs no heat and generates no heat. The volume of mixing is also 0. If you mix 50 milliliters of A with 50 milliliters of B, you get exactly 100 milliliters of solution. We can model the vapor pressure of these perfect mixtures using a mathematical predictor, Raoult's law. Looking at this graph of vapor pressure plotted against the mole fraction of the liquid, Raoult's law dictates that the total vapor pressure of an ideal solution will scale in a perfectly straight, linear line. If we plot a mixture of N-hexane and N-heptane, we see this exact linear relationship. The attractive forces match closely enough to maintain ideal behavior. But perfectly ideal solutions are incredibly rare. Most real-world chemical mixtures do not share perfectly balanced attractive forces. When the new molecular interactions in a mixture are mismatched in strength, the solution becomes non-ideal. Take a mixture of ethanol and acetone. In pure ethanol, the molecules are tightly bound to one another. They form a dense network held together by strong hydrogen bonds. But when you add acetone, its molecules force their way into that network.
lodging between host molecules and physically snapping existing hydrogen bonds. The resulting interactions between ethanol and acetone are noticeably weaker than the original bonds. In thermodynamics, we measure a molecule's ability to transition into a vapor phase as its escaping tendency. Because the bonds in the new mixture are weak, the molecules require far less kinetic energy to break free from the liquid state. Molecules escape the liquid surface at a significantly higher rate, driving the total vapor pressure of the solution far above what Raoult's law would predict. This elevated vapor pressure is defined as a positive deviation. If we look at the vapor pressure graph for this non-ideal solution, the straight dashed line represents Raoult's ideal prediction. The solid curve arching distinctly above it shows the actual elevated vapor pressure of the mixture. Microscopic structural weakness directly generates an unexpectedly high macroscopic vapor pressure. The inverse scenario occurs when two liquids mix and create stronger chemical bonds. This happens when you combine phenol and aniline. In this mixture, the proton from the phenol and the nitrogen's lone pair on the aniline lock together, forming a new intermolecular hydrogen bond. These new attractive forces are substantially stronger than those in the pure liquids alone. The molecules pull tightly together. This secures them in the liquid phase and drastically reduces their escaping tendency. Because fewer molecules can vaporize, the total vapor pressure of the solution drops significantly below Raoult's ideal mathematical prediction. We classified this tight binding behavior as a negative deviation from Raoult's law. This graph maps the negative deviation. The dashed line is the ideal baseline, and the solid curve dipping deeply below it shows the actual suppressed vapor pressure of the phenol-aniline mixture. Strengthened microscopic attractions act as an anchor, physically suppressing the vaporization of the entire solution. Now we can apply this thermodynamic framework to the unyielding 95% limit of ethanol distillation. Ethanol and water do not form an ideal solution. The mixing breaks existing hydrogen bonds, creating a massive positive deviation from Raoult's law. If we look at the positive deviation curve for this mixture and trace the composition along the x-axis to exactly 95% ethanol, the marker aligns precisely with the absolute highest apex. This exact mathematical peak is the minimum boiling azeotrope. At this precise apex, the thermodynamics dictate a unique equilibrium. The composition of the vapor being produced perfectly mirrors the composition of the boiling liquid. Because vapor and liquid are identical in composition here, continuous heating yields no further concentration. Distillation is physically impossible. The same roadblock occurs inversely. On the negative deviation curve for nitric acid and water, the absolute lowest trough forms a maximum boiling azeotrope. Mixtures with extreme negative deviations hit their separation wall at this lowest trough, where the liquid and vapor compositions once again lock into parity. Engineering a taller distillation column won't change the outcome. The absolute limits of chemical separation are rigidly defined by the microscopic strength of molecular bonds. If you take pure water and heat it to precisely 100 degrees Celsius, it boils vigorously. But if you take an aqueous sucrose solution, water with sugar dissolved in it, heated to that same temperature, the liquid remains completely calm. Adding a substance to the water prevents it from boiling at its standard temperature. To understand why this happens, we have to define what boiling actually is. A liquid only boils when its internal vapor pressure rises enough to perfectly match the heavy downward weight of the surrounding atmospheric pressure. That atmospheric pressure is a measurable physical constant. It acts as a strict threshold. Until the liquid's internal pressure pushes back with equal force, the phase change into a gas simply cannot happen. Introducing any non-volatile substance, like sugar or salt, disrupts this equilibrium. The presence of the solute lowers the liquid's internal pressure, meaning the temperature must be raised even higher to bridge the gap. Measuring this exact temperature shift provides a highly precise mathematical tool. By tracking how much the boiling point changes, we can calculate the exact mass of the invisible, unknown molecules dissolved in the water. We classify these phenomena under a specific term, colligative properties. The word is built from Latin roots, co meaning together, and ligate meaning to bind. This animation shows the defining rule of a colligative property. It depends strictly on the ratio of solute particles to total particles, completely ignoring the chemical identity of the solute. If you add 100 particles of salt to one beaker and 100 particles of sugar to another, the drop in vapor pressure is identical. The quantity of the particles dictates the physics, not their chemical nature. There are 4 interconnected colligative properties governed by this rule: the relative lowering of vapor pressure, the depression of the freezing point, the elevation of the boiling point, and the osmotic pressure. Our focus here will isolate the direct physical pipeline between the first and the third, how the lowering of vapor pressure forcefully dictates the elevation of the boiling point. Because these properties operate on strict numerical ratios, they allow us to use macroscopic phase changes, like boiling, as direct sensors for microscopic particle counts. This animation maps the microscopic baseline of a pure solvent. At the surface line, volatile liquid molecules, the blue spheres, possess enough kinetic energy to constantly break away into the empty space above. This continuous escape creates the pure vapor pressure. Now observe what happens when non-volatile solute particles, the red spheres, are introduced into the system. They disperse throughout the liquid, and crucially, many of them take up positions directly on the surface boundary. These new solute particles physically occlude the surface area. They block the upward path of the solvent molecules, effectively trapping them in the liquid phase and significantly dropping the escape rate. As a result, the space above the liquid becomes sparse. Fewer gas molecules mean less force exerted back down on the surface. This physical deficit is the literal lowering of the vapor pressure. Adding a solute crowds the phase boundary. It restricts the solvent's ability to transition into a gas, reducing its outward pressure. The chemist François-Marie Raoult established the mathematical framework for this surface crowding. Raoult's law states that the vapor pressure of a solution is directly proportional to the mole fraction of the solvent present. This clean typographic layout displays the core equation derived from his work. It shows that the relative lowering of the vapor pressure, the change in pressure divided by pure pressure, equals x2, the solute's mole fraction. That mole fraction, x2, expands into the raw number of moles, N2 for the solute, divided by the system's total moles, N1 plus N2. For highly dilute solutions, we can apply a mathematical shortcut. Because the solute moles are incredibly small, N2 is ignored in the denominator. Expanding the moles into mass and molar mass yields our final working relationship. This specific algebraic chain isolates our variables. It links a physical, measurable drop in an invisible gas pressure directly to the calculable masses of the substances involved. This chart maps the relationship between vapor pressure on the y-axis and temperature on the x-axis. The horizontal dashed line at the top represents the constant threshold of 1.013 bar, standard atmospheric pressure. As the pure solvent heats up, its vapor pressure rises along this upward curve. The exact moment this curve breaches atmospheric pressure, the liquid boils. We mark this temperature on the x-axis as Tb0. However, Raoult's law forces the pressure curve of our solution to sit permanently below the pure solvent curve. The gap between them is the pressure drop, delta P. Because the solution begins at this lower pressure deficit, it must travel further along the temperature axis to build enough internal force to reach 1.013 bar. This second intersection point marks the new elevated boiling point of the solution, labeled here as Tb. The physical gap between these two temperatures on the x-axis is defined as delta Tb, the formal elevation of the boiling point. Because vapor pressure is structurally suppressed at the molecular level, the system requires additional thermal energy to bridge the pressure deficit and achieve a boil. Experiments prove that for dilute solutions, this temperature shift, delta Tb, is perfectly proportional to the molal concentration of the solute. Molality is a specific measure of concentration. It represents the number of moles of solute dissolved per kilogram of solvent. To equate these values, we use the Ebulius-Spapik constant, or Kb. This constant is a unique thermodynamic fingerprint for every different solvent, calibrating the exact proportional relationship between concentration and boiling point. Capturing this precise temperature gap in the lab does not require complex machinery. It requires little more than highly accurate temperature tracking, like reading the fine gradation marks on a laboratory thermometer. The equation delta Tb equals Kbm serves as a critical bridge. It translates pure theoretical thermodynamics into physical data that we read directly off a lab bench. Starting with our bridge equation, the molality variable, m, expands into its measurable components: mass of the solute, W2, mass of the solvent, W1, and molar mass. By rearranging, we isolate our target, m2, the exact molar mass. We can apply this exact formula to a real-world scenario. Take a known mass of pure benzene and measure its slight boiling point elevation after adding 0.5 grams of an unknown known volatile solid. Plugging in those physical weights, the known constant for benzene, and the single thermometer reading yields the precise molecular weight of the solid, 170 grams per mole. Colligative properties provide a rigorous analytical tool. They allow chemists to decode the exact mass and identity of an unknown substance merely by observing the physical resistance it creates when we try to make a liquid boil.
Place pure water and salt water side by side in a freezer. At 0 degrees Celsius, the pure water rapidly crystallizes into a solid. Meanwhile, the saltwater solution remains entirely fluid. Freezing represents a precise thermodynamic condition, a state where the solid phase and the liquid phase exist in dynamic mechanical equilibrium. The physical metric driving dynamic equilibrium is vapor pressure. Even in a solid state, every substance exhibits an outward escaping push of molecules. A phase change into a solid only occurs when the liquid's vapor pressure perfectly matches the solid's vapor pressure. When we dissolve a non-volatile solid, like glucose, into the liquid, we disrupt this mechanical balance. The resulting vapor pressure drop forces the temperature required for freezing to fall. We are going to map exactly how this pressure drop mathematically shifts the freezing point. Then, we will use that exact temperature shift to calculate the precise molar mass of a completely unknown substance. The freezing point is a delicate mechanical balance of pressures that we can intentionally engineer to our advantage. Raoult's law provides the physical mechanism for this change. Adding a non-volatile solute directly decreases the overall vapor pressure of the solvent, as solute particles physically inhibit solvent molecules from escaping. Figure 1.8 plots vapor pressure against temperature. The steep downward curve represents the solid solvent. The gentler upper curve is the liquid solvent. Their intersection is the standard freezing point, T0F. Applying Raoult's law, the dissolved solute lowers the liquid's vapor pressure, physically shifting the entire liquid curve downwards. The new liquid curve intersects the solid curve further left on the temperature axis. This new intersection determines the solution's freezing point, labeled TF. The horizontal distance from the original freezing temperature is the depression in freezing point, denoted as delta TF. Freezing point depression is a geometric inevitability. Lowering the vapor pressure delays the intersection of the two phases, forcing the liquid to reach a lower temperature before it locks into a solid. For dilute ideal solutions, this measured drop in temperature is strictly proportional to the concentration of the solute particles within the solvent. We calculate this using a concentration metric called molality, represented by a lowercase m. Molality is the number of moles dissolved per kilogram of solvent. This gives us the foundational equation for freezing point depression. Delta TF equals Kf times molality. We identify Kf as the proportionality constant, the freezing point depression constant, or cryoscopic constant. The value of Kf depends entirely on the specific nature of the solvent. The solvent determines the constant, regardless of the solute added. Table 1.3 shows the constants for common solvents. Water has a freezing point depression constant of 1.86. Benzene, however, shows a much higher constant of 5.12. Kf acts as a thermodynamic fingerprint, dictating how aggressively a specific solvent's freezing point will drop when a foreign substance is introduced. We can expand this basic mathematical relationship into a practical laboratory tool, creating a molecular scale to weigh invisible particles. Equation 1.31 unpacks the molality term. Molality is derived from the mass of the solute, W2, divided by its molar mass, M2, all situated over the solvent's mass in kilograms, represented as W1 over 1,000. Substituting this expanded definition of molality directly back into our core freezing point depression formula produces a complex fraction. To find the unknown molar mass, M2,
we rearrange the equation, swapping M2 and delta TF. This yields our final operational formula. Molar mass is now completely isolated against measurable laboratory variables. By simply weighing initial ingredients and measuring a downward shift in a thermometer, we can mathematically determine the exact mass of a single molecule. We will now apply this model to a practical laboratory problem using benzene. A scientist takes exactly 1.00 gram of an unknown solute and dissolves it into 50 grams of pure benzene. As the mixture cools, the thermometer reveals that the freezing point of the benzene has dropped by exactly 0.40 Kelvin. Example 1.10 provides the known weights and the temperature drop for this experiment. We combine these with benzene's established cryoscopic constant of 5.12. Feeding these experimental values into our derived molar mass formula, we multiply the constant by solute mass and 1,000, dividing by the temperature drop and solvent mass. The arithmetic resolves, proving the unknown solute has a molar mass of precisely 256 grams per mole. A macroscopic observation of a chilling liquid has successfully provided the microscopic identity of an unknown compound. This leaves a fundamental question. Why did benzene react so aggressively with a constant of 5.12, while water resists with a constant of only 1.86? This formula in equation 1.37 shows that Kf is mathematically derived from the solvent's deep thermodynamic properties. Specifically, the denominator, the enthalpy of fusion, governs the outcome. The energy required to melt a pure solvent directly dictates how strongly it resists freezing point depression. We've built a complete causal chain, beginning with the physical addition of a solute into a solvent. This triggers Raoult's law, dropping the vapor pressure. That drop forces a lower phase intersection, resulting in the measurable freezing point depression. Because every step in this sequence is mathematically proportional, the final temperature accurately reflects the initial concentration. Colligative properties are reliable mathematical instruments. By reading the physical shifts on a phase diagram, we can calculate the hidden mechanics of the molecular world. If you place a wilted flower in fresh water, its petals firm up. Submerge a raw mango in saltwater brine, it shrivels into a pickle. Despite looking completely different, both of these changes are driven by the exact same physical mechanism. The plant cells in the flower and the flesh of the mango share a common structural feature. Their contents are enclosed by boundaries. In chemistry and biology, we call these boundaries semi-permeable membranes. These membranes occur naturally in organic materials like parchment, and we manufacture them synthetically as thin films like cellophane. The human body relies on them constantly. When a person consumes excess salt, water shifts across these tissue membranes, causing the physical swelling known as edema. All of these macroscopic changes in volume, the swelling and the shrinking, are visible evidence of an invisible thermodynamic drive pushing water across a barrier. This diagram illustrates what is happening at the submicroscopic scale. To the naked eye, the membrane appears to be a continuous, solid sheet, but at this level it is filled with a network of tiny pores separating a pure solvent from a concentrated solution. Because water molecules are remarkably small, they easily navigate through these microscopic holes and cross the barrier. The larger, more complex solute molecules dissolved in the solution are physically too wide to fit through the pores. They bounce off, trapped on their side of the membrane. This physical restriction creates a one-way street. Solvent molecules spontaneously flow from the region of lower solute concentration into the region of higher solute concentration. This specific flow is called osmosis. Through osmosis, the system attempts to dilute the concentrated side until the ratio of water to solute is equalized, driving both sides of the barrier toward perfect thermodynamic equilibrium. Because this flow of water is constant and directional, it generates a physical, measurable force. We can observe this force in a laboratory using a thistle funnel. The funnel contains a concentrated solution, is sealed with a semi-permeable membrane, and submerged in pure water. As osmosis drives water in, the fluid level visibly rises. Gravity pushes back, but the water climbs until thermodynamic equilibrium is finally attained. Now imagine a U-tube separated by a membrane.
By pressing a mechanical piston over the concentrated solution, we apply enough external pressure to perfectly halt the flow of water. This exact excess pressure required to prevent the passage of solvent is defined as the osmotic pressure, P. Osmotic pressure is a colligative property. Its magnitude depends entirely on the sheer quantity of solute particles suspended in the fluid, regardless of chemical identity. Because pressure directly correlates to the number of particles, chemists use this force as a mathematical tool to calculate the exact weight of invisible molecules. This foundational equation states osmotic pressure, P, equals the solution's molarity, C, times temperature and the gas constant, R. We expand molarity into moles of solute divided by volume. Next, we replace moles with the measurable weight divided by molar mass. By rearranging the equation, we isolate our target. Molar mass equals the solute's weight times R times T, divided by osmotic pressure times volume. Other methods for determining molar mass require boiling or freezing the solution. Because osmotic pressure is measured at room temperature, it is the only safe mathematical method to weigh fragile biological proteins without destroying them. The exact same thermodynamic rules that chemists use to calculate polymer weights also directly govern the survival of human blood cells. This photograph shows an intravenous drip. The fluid inside a red blood cell has an osmotic pressure equivalent to a 0.9% sodium chloride solution. When an IV fluid matches this concentration exactly, it is called an isotonic solution, allowing water to pass safely without changing the cell's shape. If injected with a hypertonic solution, where salt concentration exceeds 0.9, then we apply an immense external pressure to the seawater side, a force significantly greater than its natural osmotic pressure. This extreme pressure breaks the natural rule of equilibrium. It physically squeezes pure water molecules out of the seawater, forcing them to flow backward against the concentration gradient into the freshwater chamber. Executing this requires advanced material science. We use tough synthetic films, like cellulose acetate, which are structured to withstand crushing mechanical pressures while remaining completely impermeable to the trapped salt ions. By applying enough physical force, we actively stripped the solvent away from its solutes. Engineers translate this microscopic mechanical override into vast industrial infrastructure. As shown in this photograph, banks of high-pressure tubes are the standard technology for global seawater desalination. These massive plants generate the immense pressures required to physically squeeze the ocean, separating pure, drinkable water from the concentrated brine. Many nations now rely entirely on this scaled-up physical chemistry to meet their daily requirements for potable water. By understanding the submicroscopic rules of solvent flow, we gained the ability to weigh the building blocks of life, protect human cells, and extract potable water directly from the sea. The core rule of colligative properties is straightforward. When you dissolve a substance into a liquid, the changes to that liquid's boiling or freezing points depend entirely on the total number of solute particles. The chemical identity of those particles is entirely irrelevant. If you dissolve exactly 1 mole of a non-electrolyte, like glucose, into 1 kilogram of water, the boiling point of that water increases by exactly 0.52 Kelvin. The math holds up perfectly. But run that exact same calculation with 1 mole of potassium chloride, a standard salt, and the physical results break the equation. The boiling point elevation is 1.04 Kelvin, exactly double the expected value. If we blindly trust our standard thermodynamic equations here, we would work backward from that boiling point and conclude that 1 mole of potassium chloride has a mass of roughly 37.25 grams. We know for a fact the true molar mass is 74.5 grams. Slight pause. Chemists call this phenomenon abnormal molar mass. It is a condition where the experimentally determined mass of a solute diverges wildly from its known chemical formula. Our standard equations assume a mathematically perfect, non-interacting universe, but reality is messy. To accurately model physical solutions, we have to correct our thermodynamics. The first physical mechanism that ruins these ideal equations is ionic dissociation. When a crystalline lattice like potassium chloride drops into water, it physically separates. Every single unit splits into an individual potassium cation and a chloride anion.
You put 1 mole of lattice in, you get 2 moles of active particles out. Because colligative properties only count the number of particles, this physical multiplication doubles the expected boiling point elevation. When you run that inflated number back through the standard equation, it artificially cuts the calculated molar mass in half. The opposite effect happens in solvents with low dielectric constants. Here, we encounter a molecular association. If you drop ethanoic acid into benzene, the molecules do not dissociate. Instead, hydrogen bonds cause them to snap together into pairs. We call these paired structures dimers. This dimerization physically halves the total number of free particles floating in the solution. Consequently, the observed freezing point depression is half of what we expect, which causes the math to output an experimental molar mass that is twice the actual value. The physical behavior of solutes, whether they are splitting apart into ions or clumping together into dimers, breaks the core assumption that a mole of substance always yields a mole of independent particles. In 1880, the Dutch physical chemist Jacobus Henricus van 't Hoff formalized a mathematical solution to this particle paradox. He introduced the van 't Hoff factor, designated by the variable I. It is defined as the exact ratio of the observed colligative property divided by the theoretically calculated property. Alternatively, you can calculate I by taking the normal expected molar mass and dividing it by the abnormal experimentally determined molar mass. The boundaries of this factor map directly to the physical behavior of the molecules. I is greater than 1 for salts that dissociate, less than 1 for dimers that associate, and exactly 1 for ideal non-electrolytes that do neither. This single variable must be injected as a mandatory multiplier into all standard colligative equations. Whether calculating vapor pressure lowering, boiling point elevation, freezing point depression, or osmotic pressure, I sits right next to the concentration. By integrating this scalar multiplier, our macroscopic equations finally account for microscopic physical interactions. But even with this correction, we hit another layer of physical reality. A strong electrolyte like sodium chloride splits into exactly 2 ions. Yet, if you measure it in the lab, its van 't Hoff factor rarely equals exactly 2. This chart displays the empirical van 't Hoff factor values for various salts at different molal concentrations. If we look at the top row for sodium chloride, we see the real-world measurements. At a concentration of 0.1 mole, the I value for sodium chloride is only 1.87. It falls significantly short of complete dissociation. The physical cause is interionic attraction. In concentrated solutions, oppositely charged ions are forced into close proximity. They pull on each other, functionally reducing the number of independent active particles. We see this clearly with magnesium sulfate, where higher charge density pulls the factor down to 1.21. If we track the data horizontally toward the highly dilute 0.001 molal column, the ions spread out. The physical distance between them increases, their mutual attraction drops, and the measured values finally approach their theoretical integers. Complete dissociation is a theoretical limit, only truly reached at infinite dilution. In everyday chemistry, reality is a sliding scale governed by atomic proximity. We can actually run this logic in reverse. Instead of just correcting an equation, we can use the van 't Hoff factor to map the exact behavior of a weak electrolyte, like acetic acid, which only partially dissociates in water. Consider a specific concentration of acetic acid, where the theoretically calculated freezing point depression is 0.0197 degrees Celsius. When measured in the lab, the observed depression is slightly higher, at 0.0205 degrees. By dividing the observed depression by the calculated depression, we find our experimental van 't Hoff factor is 1.041. We map out the equilibrium state by defining X as the unknown degree of dissociation. For every splitting molecule, we get undissociated molecules, N in 1 minus X, alongside NX moles of acetate ions and NX moles of hydrogen ions. Summing those 3 expressions together gives us the total number of particles at equilibrium, which simplifies to the expression 1 plus X. Because that expression represents the multiplier for our total particles, we can set 1 plus X exactly equal to our experimental van 't Hoff factor of 1.041. Solving for X yields 0.041. This single number tells us exactly what is happening in the beaker. Precisely 4.1% of the acetic acid molecules have physically separated into ions. By plugging that percentage back into our concentration values, we can calculate the exact molarity of every ion in the solution, which then yields the precise acid dissociation constant. We just deduced the exact percentage of invisible molecular dissociation using nothing but a fraction of a degree change in a macroscopic freezing temperature. We started with a macroscopic anomaly on a thermometer. Following the math, we reverse engineered the invisible atomic interactions occurring within the solvent. Physical realities, like hydrogen bonds snapping dimers together or opposing ionic charges pulling particles close, dictate how a solution behaves. They cannot be ignored in our thermodynamic models. The Van 't Hoff factor is the essential bridge. It tethers our perfect mathematical theories to the messy, interacting reality of the physical world. These colligative properties serve as forensic diagnostic tools, allowing us to use macroscopic data to accurately measure the hidden structural dynamics of the universe.